The first step in solving the modified Atwood machine problem is to use kinematics to figure out the acceleration of the block. Based on our measurements in class, the initial velocity is 0. The displacement was 0.9 meters. And the time it took to slide up the ramp was 2.47 seconds. Rearranging the equation, we get an equation: acceleration is equal to 2 times the displacement divided by time squared. And plugging in the values that we measured, the acceleration comes out to 0.295 meters per second per second. The next step is to identify all of the forces on the objects. So the easiest is the object that is moving downward, the red block. It is experiencing a force of gravity, and we'll call that M1G, this being object 1. And it is experiencing a force of tension pulling it up. The other block is experiencing a force of gravity. We'll call that M2G, a normal force, a force of friction, and tension. And the tension experienced by this block is the same as by that. Because this ramp is at an angle, you'll notice that 3 of these 4 forces are either parallel or perpendicular to the slope, and only one of them is tilted. So we will benefit from redrawing this diagram to line up with an x and y axis that are tilted. So let's do that next. Block number 2 has 4 forces: friction force, normal force, tension, and weight. Now we need to break weight into an x and a y component. So I need to know the extent to which that goes down and the extent to which it goes across. And using the angle that we measured, I can use my trig functions to show that the down piece is mg cosine theta and the across piece is mg sine of theta. This piece here being opposite the angle and this piece here being adjacent. Therefore the cosine there and the sine there. And now I can add my other object here, the hanging object, which I swing up to line it up with the same axes as the object that's on the slope. By focusing on the entire system of 2 objects attached to each other, the force that I don't know about, tension, cancels out because it's inside of the system. The normal force and mg cosine theta cancel out because they are opposite each other. And so I've reduced my forces to m1g, m2g sine of theta, and friction. So I have a tug of war between those three forces. So continuing to focus on the system, we have two pieces of information we know. The net force on the system is the mass of the system times the acceleration of the system, and the net force on the system is this tug of war. And we see that we have one force pulling to the left here and two forces pulling to the right. And since the object moves this way, we know that this force is winning. That gives us an equation which is m1g minus m2g sine theta minus the force of friction. The definition of friction is mu times the normal force. So we can replace this variable by mu and the normal force. And the normal force is the same as the y component of weight. So if I erase if I replace FF with mu times the normal force, which is m2g cosine of theta, I can now see that I have a way to get to an answer for what is mu. Starting with things that I know. I know the mass of the system. I know the acceleration of the system, the mass of the first object in g, the mass of the second object in g, the angle, the mass of the second object, g again, and the angle again. The net force of the system and the net force of the system, figured out in two different ways, need to be equal to each other. So at this point now it's just a bunch of algebra and then plugging in the numbers that I measured. Rewriting so that all the variables that I know are in the equation, and then rearranging by bringing this to that side to get rid of the negative. I will have mu m2g cosine of theta equal to m1g minus m2g sine theta minus MSAS, the mass of the system and the acceleration of the system. And now I continue my algebra to solve for mu. And at this point I have an equation that will get me mu, and I just need to plug in the numbers that we measured. Plugging in our numbers, we get mu equals 0.2 times 10 minus 0.42 times 10 times the sine of 10 degrees minus the system mass, which was 0.62, times the acceleration of the system, 0.295. And that is all divided by the mass of the second object, 0.42, times 10 times the cosine of 10. Plugging in numbers, I get 2 minus 0.729 minus 0.183 over 4.136. That gives me 1.088 divided by 4.136, which is mu equals 0.263, and there are no units for mu. And we have an answer. Now it's possible to go about this in a different way. If I go back to my original picture here, I was able to ignore tension because it was inside the system, but it's possible, and maybe a little less complicated, to get the acceleration and then use that to find the tension in the string, and then focus on just one object at a time. Alternately, rather than following through this crazy algebra here, it would be possible to plug the numbers in along the way so that I didn't end up with a mess of an equation to deal with at the end. Either way, you should come to the same answer, 0.263.